here. Okay, and they are all, when they appear on the limb, then you can see that they are all projected approximately 100,000 kilometers above the photosphere. They enter into the coronal level. So they are all the linking feature from the chromosphere to the chromosphere to corona. Okay, if you look into the density is pretty large, 100 times more than the corona. And temperature, it is 100 times less than the corona. Density is very high. Temperature is very low. How it is suspended? How it is suspended? It is shielded from the surrounding corona. Okay, and if you put a feature like this, then what will happen in the corona? It will be diffusing instantaneously. It is not happening. So it is going to remain for few days. Okay, so how it is going to remain for few days? It's mainly because that they are all cool, dense plasma confined to magnetic sheets. So this magnetic field is shielding this material from the gravity and as well as from the surrounding high temperature corona. Okay. Sometimes what happens actually is these prominences, okay, they erupt. And why they erupt? So underneath this HF element, if you see, then what happens actually is the sunspots, they keep moving. The flows in the sunspots, the sunspot itself will be moving. Again, the plage motions, sunspot, that you call it as sunspot motions. Sunspot motions, how we can detect in the sense from the orientation from one day to the next, from the orientation from time to time. If you keep on watching it, then we'll be able to see the sunspot's orientation changes. As the sunspot orientation changes, you can say that it has a rotational motion or it has a lateral motion and so on. So these sunspot motions in the photosphere, or otherwise in the chromosphere you have plages. The plages, they don't have a specific structure, shape like that of sunspots. I think you can see as the magnetic panel expands and then goes into the chromosphere, you'll be able to see the features spreading across. The plages, actually, as the magnetic field goes up, sunspots, they have a magnetic field to the level of around 4,000 to 5,000 miles, which I mentioned yesterday. Okay, and whereas when you look into the magnetic field of what you can say the plages, there will be a order of around 100 Gauss, but still a magnetic field strength-wise, it is much more than the surrounding regions. Okay, but up in the atmosphere, the magnetic field it weakens. Okay, so and another important aspect is how to detect this magnetic field. I am talking about the strength of the magnetic field. You know the Zeeman effect. When the electromagnetic radiation passes through the magnetic field, then what happens is it is split up into three components. One is undisturbed component, the other two are disturbed mainly because of that. And not only that, it undergoes polarization. Okay, so undergoes polarization. So this polarized light will be telling you about the direction of the magnetic field. And at the same time, the strength of the magnetic field is given by the amount of splitting. Okay, so the amount of splitting gives you and the strength of the magnetic field, and the polarized level that gives you the direction of the magnetic field. So at the same time, you have to select a particular spectral line which is sensitive for Zeeman. Mind you, all the lines are not sensitive for Zeeman effect. Okay, so only few lines which are specific atomic parameters, they are okay. That is G factor unit of study, Landé's splitting factor. So the Landé's splitting factor depends upon the total angular momentum of the electrons in the atom. Okay, so only if the particular line has got a specific Landé splitting factor, then what will happen to be able to show you the strength of the magnetic field, and the same line can be used even to detect the direction of the magnetic field. Unfortunately, in the case of the sun, most of the spectral lines which are sensitive to the magnetic field, not most, almost all, okay, they all originate only from the photosphere. Okay, only from the photosphere. So the chromosphere and the coronal magnetic field lines, if you would like to measure, it will be extremely difficult. You can only extrapolate from the magnetic field what you measured on the photosphere. Because the longitudinal magnetic field component, it will be easier for you to detect if that particular spectral line is sensitive for the magnetic field. So unfortunately, all the magnetic field lines which are sensitive for the magnetic field, they are of photosphere origin. So it is not possible for us to precisely, but still what people do is the other effects, because the lines which are sensitive for magnetic field in the chromosphere and corona, they are sensitive for the other kinds of broadening like thermal broadening, pressure broadening, and so on and so forth. Doppler, the same line is sensitive for magnetic field, the same line is sensitive for Doppler field. Okay, then how is it possible for you to say this broadening comes mainly from the Doppler or from the Zeeman? You do not know. So, but still people are trying to, what I can say, eliminate the factors due to the Doppler and the thermal broadening as well as pressure broadening, and then they are trying to get only the Zeeman, okay, component alone, but they are finding it extremely difficult. Okay, Mona Haigar, if NASA, she worked as a here on 20 years. Okay, so even then she is unable to succeed. Although she developed electromagnetograph. Electromagnetograph is an instrument which can detect the magnetic field strength of a particular feature on the sun, like sunspots or flages or filaments and so on and so forth, and as well as the direction of the magnetic field. Okay, somehow she was able to succeed in only in detecting the transverse component of the magnetic field. Longitudinal component is the line of sight component of the magnetic field. Transverse means the component perpendicular to that. How to measure that? We will have to go to the other side of the sun and then measure this. Is it possible? It's not possible. Okay. So, and of course she was able to extrapolate from the longitudinal component to some extent the transverse component. And that's why people are finding it extremely difficult to build a electromagnetograph, okay, successfully. Even today, it is extremely difficult. Because people, they use H-alpha line, but H-alpha line, it is neither sensitive to magnetic field, but at the same time I told you yesterday, it is sensitive to temperature, highly sensitive to temperature. Okay, to some extent it is sensitive to magnetic field also, but the other factors also influence. So they are trying to eliminate one by one, and finally they would like to get only the magnetic component alone. And if you do that kind of interactive technique, then eventually you may not be able to project the correct picture. Somewhere you miss. That's why predicting the solar flash and coronal mass ejections has become extremely difficult, but even then you can say still, so then it is likely to occur. Okay? It is not possible to say precisely today at what time it is going to occur. How can you say that on 26th of or 21st of December 2012? This cannot happen. You hold a rubber and then you keep on testing it. Finally what happens, the rubber is thrown out. So exactly like that, the magnetic twist is inducted into the prominence, and because of the sunspot motions or the powerful eruption occurs, and then enormous amount of materials that will be thrown out. So that's called as active prominence. Okay, these are all called as quiescent prominences. Okay, quiescent prominences. Now, solar flash. The next phenomena. We have seen the first phenomena, what the tangent phenomena, solar prominences, and how they erupt. And the next one is the solar flare. Solar flares, they are all energetic phenomena that takes place in the solar atmosphere. Okay, they are all explosions or storms in nebulous plasma. They are all associated with one or two activities in the sun. Okay, they are all associated with sunspots. See, though these flares are coronal phenomena, underneath that, okay, so the sunspot is present. If you watch from wave, they occur in the localized region of the solar atmosphere. They never occur all through the corona. They occur only from a particular region in the corona. Underneath the region, if you look, then you will be able to see either the presence of sunspots or the presence of a large, or the presence of a filament. Okay, so either of these three active regions will be present, and these regions, okay, they have magnetic shielding. Okay, so they have material in the magnetic field. So they are all explosions or storms that are taking place in the magnetized plasma in the solar atmosphere. Okay, that is, the material in those active